Another example. Let's say we want the integral from 0 to pi of cosine theta d theta. The cosine function is continuous, and therefore it's in particular continuous on the interval 0 pi. So all we need to calculate this definite integral is the indefinite integral, in other words, an antiderivative. So a function whose derivative is cosine, we know what that is. Antiderivative of cosine is sine. So that means that my integral is simply the sine function that I'm going to evaluate between pi and 0. So I get the sine of pi minus the sine of 0. But both values are 0, therefore I get 0. That might be a little bit surprising that I integrate a non-zero function and I get 0 for the integral. If you draw the picture, it's not surprising at all. This is the graph of the cosine function on 0 pi. And you see that from 0 to pi over 2, cosine is positive, and the green area corresponds to the integral of cosine from 0 to pi over 2. The blue area corresponds to the integral of cosine from pi over 2 to pi. Of course, I have the same area above and below the x-axis, and they cancel each other out. In other words, we could have figured out by a geometric argument that this integral is 0 without even knowing the fundamental theorem of calculus. But you see that here we can just get our answer without thinking very much once we have this fundamental theorem of calculus as a tool. Okay, let's say that now I want to integrate from 0 to pi over 4 secant squared t. So according to the fundamental theorem of calculus, to calculate this kind of definite integrals, we only need to find an antiderivative of the function. And a function whose derivative is secant squared, we know that is tangent. So the integral from 0 to pi over 4 of secant squared is simply tangent x or tangent t evaluated between 0 and pi over 4. So I get tangent of pi over 4 minus tangent of 0. Tangent of pi over 4 is 1, tangent of 0 is 0, so this integral is 1. Now with this kind of function you have to be a little bit careful. In this case we have no problem applying the fundamental theorem of calculus because the function secant squared, which is 1 over cosine, is well defined and continuous on 0 pi over 4. However, if we had the same question with the integral from 0 to 3 pi over 4, then we would have to be a lot more careful, because then in the interval we would have the value pi over 2, where the cosine takes a value 0, which means that secant squared goes to infinity when secant squared of t goes to infinity when t gets close to pi over 2, which is a value in the interval. So in that case, the fundamental theorem of calculus would not apply because the function is not continuous on the interval. Another example. We want to integrate from 0 to 1 the function 3 plus x root x, and again the idea of the fundamental theorem of calculus is that for a continuous function like this one on an interval, all we need to calculate the definite integral is an antiderivative of the function. If we want an antiderivative, this x root x is going to be more handy if we write it as x to the 1 times x to the 1/2, in other words x to the 3/2. So now I'm integrating from 0 to 1 the function 3 plus x to the 3/2, and I know how to find an antiderivative for that. Antiderivative of 3 is 3x, and of x to the 3/2 is x to the 3/2 plus 1, which is 3/2 plus 2/2, 5/2, divided by 5/2. In other words, 2/5 of x to the 5/2. I need to evaluate this antiderivative function between 1 and 0, so I plug x equal 1, I get 3 plus 2/5, I plug x equals 0, I get 0, and I take the difference. So in this case we get 15 plus 2, 17/5. A slightly different kind of example. We're looking for the integral from negative pi to pi of the function f that is defined piecewise by x if x is between negative pi and 0, and by sine x if x is greater than 0 and less than or equal to pi. The first observation is that the fundamental theorem of calculus is going to apply to this function because function x is continuous, function sine x is continuous, And so the only possible discontinuity is at 0, but you see that the limit of f from the left and from the right is the same and is 0, because x goes to 0 when x goes to 0, and sine x has also limit 0 at 0. So this is a continuous function on the interval. However, it's defined piecewise, so it's not very easy to know what the antiderivative looks like globally on this interval from negative pi to pi. However, we have seen that one of the properties of definite integrals is that when I integrate from a to b, I can first integrate from a to c, and then from c to b, and add these two integrals together. So we're going to do that, cutting the interval in two pieces, from negative pi to 0, and from 0 to pi, where of course we cut at 0 because this is a place where the definition of the function changes. So now for the first integral, on the interval negative pi 0, the function coincides with a function x, and on the second interval from 0 to pi, the function coincides with a function sine x. Therefore, what we have is the integral from negative pi to 0 of x plus the integral from 0 to pi of sine x. Now each one of these two can be easily calculated using the Fundamental Theorem of Calculus, or the weak form of this theorem. Antiderivative of x is x squared over 2. Antiderivative of sine x is negative cosine x. And so I plug the value 0 in x squared over 2, I get 0. Then I subtract the value at negative pi. That's going to give me negative pi squared, which is the same as pi squared divided by 2. Then I have the value of negative cosine x at pi, that's negative cosine pi, minus the value of negative cosine at 0, that gives me plus cosine 0. Cosine pi is negative 1, so its opposite is positive 1. Cosine 0 is 1, so I get 2 minus pi squared over 2. Among the motivations to calculate these definite integrals was the problem of finding the area under the graph of a function, or various kinds of areas. So here we want to find the area bounded by the x-axis and the parabola of equation y equals 6 minus x squared. So this is a parabola that opens downward because the coefficient of the square is negative. More specifically, if you draw the picture, this is the graph of the function 6 minus x squared, and indeed this is a parabola opening downward. And so the area that is considered here is the area that is above the x-axis over the interval that looks like negative 3 to 2 and below the parabola. Now the intersection points here between the parabola and the x-axis are important. On the picture it looks like they are negative 3 and 2, but we can verify that by finding them explicitly, calculating what they are. And to this end, we set the function equal to 0, because the intersection point with the x-axis or the intersection with y equals 0, so we set y equals 0 in the equation of the parabola. And since 6 minus x squared factors as 3 plus x multiplied by 2 minus x, we see that this product is 0 if x is negative 3 or x is 2. That means that this area here is the area that we are looking for, and it can be set up as the integral from negative 3 to 2 of the continuous function 6 minus x squared. And this function is continuous and positive on that particular interval. And so the area under the graph is the area we're looking for. To obtain it, we use the Fundamental Theorem of Calculus. In other words, we just need an antiderivative of this function. Antiderivative of 6 is 6x, of x is x squared over 2, of x squared is x cubed over 3, and we want to evaluate this function 6x minus x squared over 2 minus x cubed over 3 between negative 3 and 2. The value at 2 is 12 minus 2 minus 8 third. The value at negative 3 is negative 18 minus 9 half plus 9, and this all simplifies to 1/25 1 over 25 over 6. Now turn to the next video where we're going to look into how to prove the Fundamental Theorem of Calculus.